Hello and welcome to Understanding a Confusion Matrix and Performance Metrics. My name is Lucas Kelly, and all the information that we'll be going over today you can access through my GitHub page just by following this link. And we're going to be looking at that video in a second, but you could get to my landing page here, click on repositories and the lessons repos where you're going to want to look. And you'll scroll down into the README and you'll see that the confusion matrix lesson is one we're talking about. There's a link to this video, a link to the notebook, and a link to this presentation as well. So let's get into it. We're learning today about confusion matrix. And by the end of this lesson, you should really be able to interpret a confusion matrix. You should know the difference between false positives, false negatives, true positives, and true negatives. And you should also know how to create a confusion matrix from code. So let's start here with an example. This is an example from the healthcare industry. Let's say that we created a model and the model was predicting whether or not a person had a disease. And so this is a categorization, this is a classification model, and it's really predicting a 0 or a 1 based on a maybe large set of features. If the computer predicts a 0, that means no disease is detected. And if it predicts a 1, that means the disease is detected. So it doesn't matter what kind of model you use. In this case, we used a random forest, but you could really use any model to make a prediction on a classification. And so here on the left, you see a true label. So this is what we know to be true. It could be that the doctor gave this diagnosis and we're positive that they were true. It could just be our training data set in which we built our model off of. That's most likely what will happen. And then we have on this side the predicted label. So this is what the computer said it should be based off of the features and based off of the performance of the model. So this is kind of like a times table, multiplication times table when you were in elementary school probably. You can sort of do that sort of system where, let's say we wanted to see where the predicted label was a 1 and the true label was a 1. Well, we just go up and then over to see where those two boxes coincide. That's 4,819 times in which they were both predicted as 1. So let's look at the different ways that we measure this. First, we're going to look at the true negative. Okay, so true, it's true because both the true label and the predicted label are the same. In this case, they're both zeros. So that's true. It's going to be true because they're both the same thing. And it's going to be negative in this case because no disease was detected. So that's true negative. Both the true label and the predicted label are the same, and they're both predicting a negative, meaning the person does not have the disease. So let's look and see how many of those we have. We have a 0 on the predicted label and a 0 on the true label. Back to your multiplication chart, 1,069 cases of a person not having a disease, both by the true label and by the predicted label. Great. So let's look at a case of a true positive now. So a true positive is the same thing, true because both the true and the pred are giving the same exact classification of a 1. In this case, we have 4,819 instances where that's going to happen. That's a lot of detected diseases. So, you know, this model doesn't, this example doesn't tell us what we're predicting. It just is saying 0 for no disease, 1 for disease, but that's an interesting thing to see in the data there. Now, false positive, false because this is a different one now. False because true and pred are different. So we're saying that the true gave this a non-disease classification and the pred actually said it does have the disease. So this is a false. Okay, it's false because they don't match up. And it's positive in this case because it's just simply giving a diagnosis of a disease. And in this case, it's a false positive, it's a misdiagnosis. It's misdiagnosed by the computer. So here, let's look at how many times this happened. The predicted label being a 1, a person has a disease, when really they don't have a disease in true life, the true label says no. That's 218 cases. So think about what that means. That means that 218 people, if we're measuring this in individual people, were told, they were given a scare. So they were basically scared into thinking that they had a disease by a computer model. And in truth, they really did not have the disease. And the flip side of that, again, is also going to scare some people, a false negative now. It's false negative because, again, The truth and the predicted labels are not the same. So there's one of them is wrong, basically. The prediction is wrong. It's a false negative. This is another misdiagnosis. It's false because they don't match up, the true and the pred, and it's negative because it's falsely saying that a person does not have a disease. It's falsely giving a negative label. So let's see how many times that happened. That happened 116 times. That's enough people to be, scared, probably even worse, because they were told if they were only relying on the predicted label that they don't have the disease when they actually do have the disease. So that could be pretty alarming if this model is not tuned up a little bit. Great, so that's our healthcare example. Now let's get into a baseball example. This is one of my favorite things to do, is analyze baseball data. And so I took data from a baseball game, one game in particular, and one pitcher in that game, and I measured how many balls and strike calls he was given by the umpire as compared to if a computer were actually designating those calls. So nowadays in every Major League Baseball stadium, there's a radar system, there's a computer system in the stadium that can accurately measure when the baseball crosses the plate, and that determines whether it's a ball or a strike. So let's look at an example of this in real life. This was a game against the Houston Astros and the New York Yankees. This was a big time playoff game. You're going to see Zach Greinke, a pitcher, throw a ball into the catcher, and the ball crosses the plate. It's in that box. It should be a strike. And you'll notice that it's not a strike. The umpire never gave an indication of a strike call. The count is 3-0. That means 3 balls, no strikes. So this was a very suspect situation. Watch again in slow motion. The ball clearly crosses the plate inside that white box outline that they provide on the screencast. And the umpire called it a ball. But the computer system really should have called it a strike. And there it is in our confusion matrix. That's that one instance in that pitcher's entire game in which the umpire called a ball when the computer called it a strike. Now, for this situation, we're going to say that this is the true label. The umpire is the true label. That's because at the end of the day, it doesn't matter what the computer says. The umpire is the one who's making the call. The computer, let's just say, is our predicted label. Now, the predicted is the computer. Even though the computer might be more accurate nowadays, we're still not using it in the sense. So it's not the truth. It's more of a predictor. So with that in mind, now we're going to continue in interpreting confusion matrix and test yourself with this question. So we know, how many times did the umpire designate a ball when the computer designated a strike? So umpire ball, let's go here, umpire ball, and let's see when the computer called a strike, computer called a strike. Okay, that was one time. That's the video that we saw. Now, knowing that a strike, in this case, is a positive and a ball is a negative. I'll say it again. A strike is a positive, ball is a negative. And think of that because it's from the pitcher's point of view. A strike is a good thing, a positive. Just kind of think of it like that. And a ball is a negative. So we're trying to detect strikes here. So knowing this one instance, called strike by the computer, called ball by the umpire, how would we classify this one instance? So I'll give you 5 seconds. Just think to yourself and try and make a guess. Is that a true positive, a true negative, a false positive, or a false negative? If you guessed false positive, you were correct. And it's a false positive. Again, it's false because they don't match up. The true and the pred don't match up. Let's go back to look at what that means. False positive, here it is. True is a 0 or a ball, and the pred is a 1, a strike. And in this case, a false positive because the computer falsely categorized that pitch as a strike. Even though you might think, well, the computer looks like it was actually the one that was right. Again, remember, the umpire is the one who we're using here as the true label. The computer is the pred. So in this case, the computer falsely categorized that pitch as a positive or a strike. Okay, another situation using the same confusion matrix. How many times did the umpire and computer both designate a called strike? So here's the umpire, here's the computer. We have that happening 14 times. Now, in your head, try to classify this as true positive, true negative, false positive, false negative. I'll give you 5 seconds to do that now. And if you guessed true positive, you're right. remember, the umpire and the computer in this situation matched up. So that's what makes the true. And it's positive because they both called a strike, a positive for the pitcher. Okay, so let's go now to a Jupyter notebook that will show how to create a confusion matrix. So really, there's a lot in this notebook. I would recommend that you go back and sort of read it step by step. I just kind of outlined and make an important point here that building a confusion matrix really cannot happen until you've done these things. You've cleaned your data, you've processed it, you've explored it, and now you have created a model which you're trying to evaluate using a confusion matrix. So the libraries that I use in this notebook are just Pandas, scikit-learn, which builds the confusion matrix, itertools, matplotlib for visualization, and NumPy to do a little calculating. So this example data set is created for you and it's in the repo. It's just basically a pitch by pitch of this game, every single pitch and the features that are shown by pitch. And I clean it up a little bit because we don't need all of them for this purpose here. So you have at bat, inning, pitch frame. There's all kinds of stuff here that you might not really need. What you need to focus on though are the designated, that's the umpire, designated ball. And then comp call, short for computer call, is a ball as well. So these are the two columns or the two features that we're trying best to focus on. We're really focusing on these. And the des, remember, is the true label. The comp call is the pred, or the predictor in this case. And I also just went ahead and I spliced it again so that it's only showing that one picture that you saw in the video of Zach Greinke. So when we come down, we scroll down, we look at this in the notebook, we can see that the calls match up very, very commonly. Often they match up. But here's a situation where the umpire called a strike and the computer said it should have been a ball. So this isn't the best way to visualize this information, right? So we want to come down to this box here and we want to make sure we separate and we say, okay, the true, in that case, remember, is the umpire's designation. Because at the end of the day, the umpire's call is the one that sticks. The computer is kind of like the predictor. All this stuff that we're doing with computers, it's predicting what the call should be. And that's going to be the comp call in the data set. So I'm not going to get too far into this code because I'm sort of running out of time here, but I would really encourage you to go back and go through each step. I'll kind of break it down just sort of briefly here. This is a function that's created to take the Y true, the umpire's call, and the Y pred, which we designated up here above. And it's just creating that confusion matrix based off of those two comparisons. And so this is just a way to make it, if we change this to reds, we would have like a red one. But I think blue is a little bit easier on the eyes. And I have to do this. And oh boy, I have to go up and just run all my boxes because this is a loaded data frame. You can load all this stuff up here. And it wants a capital R there, I think that's why. There we go. So, you know, the red, it's just changing the colors and how you view it. But I think the blues is actually a little bit easier on the eyes here. So let's change it back. And it's really just doing that for you. It's creating that sort of heat map so that you can visualize where the most common cases are. If we also go through here, we can see a confusion matrix, umpire, computer. These are just labels so that we can read it clearly. We come down, we make sure that the numbers go inside each box individually. And then also that if it is in this dark blue box, the number is white. And if it's in the lighter box, the number is black. And there we have our function. And then once we put in the true and the pred labels there, we can create a nice confusion matrix that we can read. That's the same exact one that we had in the presentation. And so at the end of this notebook, I also just remind you of the true positives, true negatives, false positives, and false negatives, and why we label them that way. So I hope that this lesson allowed you to meet the objectives. Let's just go through and check on that. Do you know how to build and interpret a confusion matrix? Well, hopefully you really know how to interpret a confusion matrix, but building one, you might have to go back and look at the code for that simple scikit-learn and built-in function to make your own confusion matrix of your own data. hopefully you can tell the difference between false positives, false negatives, true positives, and true negatives. Maybe you want to just look up some confusion matrices on your own and just see if you can label those correctly. And then in another lesson, whoops, I want to go back here. In another lesson, you would really want to understand how those labels relate to calculating evaluation metrics and when you should really use certain metrics, depending on what situation you are in, what your model is actually doing. If it's a healthcare data, if it's a baseball data, whatever it is, there's different ways to evaluate. So thank you very much. I hope you got something out of this and better understand confusion matrices. If you need to go back, remember that this is the GitHub repository where you can find all of this information. It's the lessons one. And if you have any questions or comments, please reach out to me on LinkedIn. I'd love to help you through some of this. Thank you. Bye.